After numerous videos on runtime organization and stack machines, we're finally ready to begin our discussion of code generation. So as I mentioned in the previous video, we're going to focus on generating code for stack machines. This is probably the simplest code generation strategy. It doesn't generally yield extremely efficient code, but it's an interesting strategy and certainly not a totally unrealistic one, and it's more than complex enough for our purposes. We want to run the resulting code on a real machine, and we're going to use the MIPS processor. In particular, we're going to use a simulator for MIPS, which runs on just about any kind of hardware, and so that'll be very convenient for the course project. And the basic idea, the basic strategy, is going to be to simulate a stack machine using MIPS instructions and registers. So the first decision in designing our simulation is deciding where to put the accumulator, and we'll keep that in MIPS register A0. Any register would have done, but we'll just use A0 always for the accumulator. And then the stack is going to be kept in memory. And I should point out here that when we talk about a one register stack machine, nominally that register, in this case A0, is the top of the logical stack of the stack machine. But just to avoid confusion in the terminology, I'm going to refer to A0 as the accumulator and the stack as all of the other data that's kept in a memory stack on the MIPS processor. So we'll just consider A0, the accumulator, to be distinct from the stack, which lives in memory. And the stack on the MIPS will grow towards the lower addresses, which is the standard convention on MIPS. The address of the next location on the stack is going to be kept in the MIPS register SP. And this register actually has a mnemonic name that stands for stack pointer. So normally on the MIPS machine, compilers use SP to point to their stack. And the top of the stack will always be at the address SP plus 4. So remember, the stack is growing towards low addresses, and the address in the stack pointer is the next unallocated location on the stack. So the stack pointer actually points to unused memory, and the top of the stack, therefore, is at the next higher word address, which would be SP plus 4. Now, the MIPS architecture is quite an old architecture. It was designed in the 1980s, and it was or is the prototypical reduced instruction set computer, or RISC machine. And the idea behind RISC machines was to have a relatively simple instruction set. Most of the operations use registers for operands and results, and then load and store instructions are used to move values to and from memory. So primarily all the computation takes place in registers, and the memory operations are primarily just loading and storing data. There are 32 general purpose registers on the MIPS. It's a 32-bit machine. We're only going to use 3 of those registers. We already talked about SP, the stack pointer, A0, the accumulator, and we'll need one more register for temporary values. So some operations that take 2 arguments, like plus and times, we'll have to have 2 registers to hold the arguments to the operation. So we'll use the accumulator for one of those and a temporary register for the other. And there's a lot more information on the MIPS architecture in the SPIM documentation. SPIM is the simulator that we will use to execute MIPS code. Now, of course, to generate code for the MIPS, we'll also need some MIPS instructions, and we'll be able to get away with just a very small number of instructions, 5 in fact, for our first example. And here they are. So the first instruction we need is load, or load word. And the way this works is it takes the value of register 2, takes the contents that are in register 2, adds a fixed offset, so this is a number that's directly in the code, adds a fixed offset to that, to the contents of register 2, that's a memory address, and loads the value of that memory address into register 1. The add instruction adds the contents of register 2 and register 3 together and stores the result in register 1 again. The store operation, or store word operation, takes the value in register 1 and stores it into memory. So that's stored at a memory address, and what's the memory address? It's the contents of register 2 plus a fixed offset that's in the code. And an add immediate unsigned does an unsigned add, and it takes a value in register 2, an immediate value, so this is just a number that's a constant that's directly embedded in the code. It adds that to the value in register 2 and stores the result in register 1. And the unsigned aspect here just means that the overflow is not checked. We're not checking whether we generate a number that's beyond what we could represent if we had signed numbers. Finally, load immediate just takes a constant that's in the code and puts it into the register that's named as the first argument. All right, so those are the 5 instructions that we need to do one very simple example. So now we're ready to do our first program, and not surprisingly, it's the same program that we looked at in previous videos when we were talking about stack machine code. And let's look, here's the program for adding 7 plus 5, written out in our little abstract stack machine language. And now our goal is to implement this program using MIPS instructions. So over here on the right, I'm going to lay out the instructions we would use to simulate this program or implement this program on the MIPS machine. All right, so the first instruction is to load 7 into the accumulator. And we can do that with a load immediate. We're going to load immediate the value 7. A0 is our accumulator register, and so this instruction puts 7 in the accumulator. Next instruction, we want to push the value of the accumulator onto the stack. How do we do that? Well, we have to store the value onto the stack, and remember the stack pointer points to the next unused memory location. And so we're just storing directly at what the stack pointer points to, so that's at a 0 offset from the stack pointer. The value of the accumulator pushes the value onto the stack. And now to restore the invariant that the stack pointer points to the next unused location, we have to subtract 4 from the stack pointer. Okay, so these two instructions together implement a push. They push the beta value onto the stack, and they move the stack pointer to the next unused address. All right, now we're ready to do the next instruction, loading 5 into the accumulator. Well, we already know how to do that. There'll be a load immediate into the accumulator register A0, the immediate value 5. And now we're ready to do the add. And how does that work? Well, first we have to load the value of that's on the top of the stack, okay, because the second argument is taken from the top of the stack. And since MIPS can only do operations out of registers, that value has to go somewhere into a register, and this is where we use our temporary register. So now this value is now at offset 4 from the stack pointer because we subtracted 4 from the stack pointer, and we load it into register T1. Okay, and then we can actually perform the add, and so we add the accumulator to the value of T1, and we store the result back into the accumulator. And finally, we're going to pop the stack, so we're done with the value that's on the stack. And how do we pop? Well, we just add 4 to the stack pointer, and that moves the stack pointer back, popping that value off of the stack.